Hello, everyone. Welcome to our deep dive podcast, where today we'll be reviewing the paper Points Reader Distillation-Free Adaptation of Vision Language Models for Document Conversion. Are you ready to explore the latest in document AI?
Absolutely. This paper is quite exciting, especially since it proposes a distillation-free approach for document conversion. To start, can you explain why high-quality labeled data is so important for document conversion models?
Of course. High-quality labeled data is essential because document conversion models need to accurately extract complex elements like tables, formulas, and multi-column text from documents. Without precise labels, models can't learn to handle these challenging scenarios effectively, which is a big problem in real-world applications.
That makes sense, but manual annotation is both expensive and time-consuming, right? And automatic labeling with existing models often lacks accuracy, especially for complex layouts.
Exactly. That's why many current approaches rely on distillation, where a student model learns from the outputs of a teacher model. However, this can limit the student's performance and cause it to inherit the teacher's biases.
So, the Points Reader paper proposes a fully automated, distillation-free framework. Can you walk us through the two main stages of their approach?
Sure. The first stage is called the Uniform Format Warm-Up Stage, or UWS. Here, they generate large-scale, diverse synthetic data in a unified format. This helps the model learn to extract key elements like plain text, tables, and formulas in a consistent way.
And the second stage?
The second stage is the Iterative Self-Improvement Stage, or ISS. In this stage, the model, which was initially trained on synthetic data, is used to annotate real-world documents. Then, a set of filtering strategies is applied to verify the quality of these annotations. The model is retrained on the verified data, and this process is repeated iteratively to progressively improve both the model and the dataset.
That's fascinating. So, instead of relying on external teacher models, they use a self-improving loop. What are the main contributions of this paper?
The authors highlight three main contributions. First, they propose a distillation-free framework for generating high-quality training data. Second, they introduce a self-improvement method that adapts models trained on synthetic data to real-world distributions without external supervision. Third, they develop a compact yet powerful document conversion model that achieves state-of-the-art performance.
Let's dig deeper into the uniform format warm-up stage. Why is unifying the output format for document elements so important?
Unifying the output format reduces the learning complexity for the model. Documents can contain plain text, tables, and formulas, each with different possible representations. By standardizing these, using Markdown for text, HTML for tables, and LaTeX for formulas, the model can focus on learning the content rather than dealing with format inconsistencies.
That's clever. How do they generate the synthetic data?
They use a large language model to generate document text based on specific prompts. For tables and formulas, they apply rule-based filtering to ensure quality. The generated texts are rendered into images using HTML templates with various layouts, and these image-text pairs are used to fine-tune the vision language model.
What about the iterative self-improvement stage? How does the model improve itself using real-world data?
After the initial training, the model is used to annotate real-world documents. The outputs are then filtered using rule-based strategies to ensure quality. For example, they use F1 score comparisons with OCR outputs for plain text, structural checks for tables, and syntax validation for formulas. Only high-quality samples are kept for retraining.
Interesting. So, the model gets better with each iteration. How do they measure the effectiveness of their filtering strategies?
They conduct ablation studies, showing that each filtering strategy, plain text, tables, and formulas, contributes to improved performance. For instance, applying the plain text filter significantly reduces the edit distance on text-related metrics.
Do they discuss the impact of data diversity and dataset size during the warm-up stage?
Yes, they do. They find that increasing data diversity by including different types of document elements improves performance. However, after a certain point, adding more synthetic data can lead to overfitting, as the synthetic layouts differ from real-world documents. This highlights the need for the self-improvement stage.
That's a valuable insight. What about the aspect ratio of the generated images? Does it affect model performance?
Absolutely. They observe that filtering out images with abnormal aspect ratios, those that are too long or too wide, improves model accuracy. This is because most real-world documents have aspect ratios similar to A4 paper.
Let's talk about the experiments. What data sets do they use for training and evaluation?
For synthetic data, they use a mix of generated samples and tables from PubTabNet. For real-world adaptation, they use Docmatics, which contains over 2 million document images from various sources. For evaluation, they use the English splits of Fox and OmniDoc Bench, which test the model's ability to extract text, tables, and formulas.
How does Points Reader perform compared to other models?
Points Reader outperforms many existing public and proprietary models, including some that are much larger. It matches or surpasses models like Quen 2.5-VL-72B on several benchmarks, especially in table recognition.
That's impressive. Do they compare their approach to direct distillation from large models?
Yes, they do. They show that their distillation-free approach outperforms models trained by distilling from Quen 2.5-VL-72B, both in terms of overall performance and computational efficiency.
What about the limitations of their approach?
The main limitations are that Points Reader currently supports only English and works best with printed fonts. It struggles with handwritten text and doesn't yet extract images from documents. The authors plan to address these issues in future work.
Let's discuss the ablation studies in more detail. How do different data types and sampling ratios affect performance?
They find that adding more diverse data types, like formulas and multi-column layouts, improves performance. However, downsampling plain text or upsampling tables and formulas doesn't help, as it reduces data diversity and can harm generalization.
How does the model's performance change over multiple self-improvement iterations?
With each iteration, both the model's accuracy and the quality of the generated data improve. The F1 score between the model's predictions and OCR outputs steadily increases, and the number of high-quality samples grows.
Do they provide any case studies or examples of how the model's outputs evolve?
Yes. They include several examples showing that the model's annotations become more accurate and complete over successive iterations. This demonstrates the effectiveness of the self-improvement process.
What about computational resources? How demanding is the training and inference process?
They use 64 NVIDIA H800 GPUs for training, and processing 1 million samples takes about 7 hours. Inference on 2 million Docmatic samples takes around 10 hours. So, while resource-intensive, it's manageable for large-scale research.
Let's talk about the prompts used for synthetic data generation. How do they ensure diversity and realism?
They design category-specific prompts for plain text, formulas, tables, and multi-column layouts. The prompts encourage the use of various markdown elements, LaTeX formulas, and HTML tables, and they randomize topics and styles to maximize diversity.
How do they handle the evaluation of complex document elements like tables and formulas?
For tables, they check structural validity, ensuring consistent cell counts in rows and columns. For formulas, they verify syntactic correctness using LaTeX parsing. For plain text, they use F1 score comparisons with OCR outputs.
Do they compare their dataset to others used in the field?
Yes. They compare their dataset to Cosmos 2.5 and OLEM OCR. Unlike those, Points Reader's dataset uses HTML for tables, which is more expressive, and doesn't rely on distillation from other models. This results in higher annotation quality.
What are some future directions mentioned by the authors?
They plan to extend Points Reader to support more languages, improve performance on handwritten text, and add support for extracting images and their locations within documents.
That would make the model even more versatile. Do they mention any challenges with data balance?
Yes. They note that most samples contain only plain text, with fewer containing tables or formulas. They experiment with different sampling ratios, but find that maintaining the natural distribution yields the best results.
How do they ensure that the model doesn't overfit to synthetic data?
By limiting the size of the synthetic dataset and focusing on real-world adaptation through the self-improvement stage, they prevent overfitting and improve generalization.
Do they provide any insights into the evolution of the model during training?
Yes. They show that the model's performance on plain text, tables, and formulas steadily improves with each self-improvement iteration, even though only rule-based filtering is used for tables and formulas.
That's a strong testament to the effectiveness of their approach. How do they handle noisy data during training?
They use strict filtering strategies to discard low-quality samples. For example, samples with low F1 scores or invalid table structures are removed before retraining.
Do they discuss the impact of loading weights from previous models versus pre-trained models?
Yes. They find that initializing from a pre-trained model yields better performance than loading weights from a previous version, as the latter may contain noise from earlier training stages.
That's an important detail. How do they visualize the improvements in data quality?
They plot the number of retained samples and the average F1 score across iterations, showing a clear upward trend in both metrics.
Do they mention any open-source resources?
Yes. The Points Reader model is available on GitHub, making it accessible for further research and development.
That's great for the community. How do they handle the challenge of evaluating reading order in documents?
They include reading order as a metric in their evaluations, particularly for multi-column layouts, and show that their model achieves strong performance in this area.
Do they provide any recommendations for future research?
They suggest exploring additional strategies to increase data diversity and further improve model performance, especially as the rate of improvement slows after several self-improvement iterations.
That's a good point. As models approach saturation, new techniques are needed to push the boundaries.
Exactly. They also highlight the importance of high-quality, diverse datasets for training robust document conversion models.
To wrap up, what's the key takeaway from this paper?
The key takeaway is that a distillation-free, self-improving framework can produce high-quality document conversion models that outperform larger, distillation-based models. By combining synthetic data generation, unified output formats, and iterative self-improvement, Points Reader sets a new standard for end-to-end document conversion.
That's a fantastic summary. This paper demonstrates that innovation in data generation and model adaptation can lead to significant advances, even without relying on massive teacher models.
Absolutely. It's an exciting time for document AI, and Points Reader is a great example of how thoughtful design and automation can drive progress.
Thanks for joining us on this deep dive. We hope you enjoyed our review of Points Reader, distillation-free adaptation of vision language models for document conversion. Stay tuned for more paper reviews and discussions on the latest in AI research.
To summarize, Points Reader introduces a fully automated, distillation-free framework for document conversion, leveraging synthetic data, unified output formats, and iterative self-improvement to achieve state-of-the-art performance without inheriting the limitations of teacher models. Thank you for listening.